In this video, we're still talking about curvature and torsion. First, I wanted to recap what we talked about in the last two videos, just briefly, and then we're going to go more into finding torsion. We talked about what it meant in the last video, and in this video, we're going to give you a couple of formulas for torsion, one that you use for interpretation, and then one that you will use practically when you're trying to solve problems, and then we'll use it to solve a problem. We'll probably find a curvature for the same curve, provided that the video doesn't get too long. So in the last two videos, we talked about curvature. First, we started by saying, well, what is curvature intuitively? We said, well, it's a measure of how curvy the curve is, which is not very technical at all, I know. But if I have a curve and it looks like this, and maybe this is the direction that we're traveling as we go along the curve, it looks something like this. Well, if intuitively I know that this is more curvy than that is, this is more curvy, that's less curvy, but it's still curvy, and that's not really curvy at all. And we also talked about this idea of an oscillating circle. That's a circle that has exactly the same curvature that fits snug against the curve at a certain point. So my oscillating circle here might look something like this. If that's R, the curvature here, that's the radius of the circle, is 1 over R. Now for this one, I can't even draw an oscillating circle because if there is any curve at all, it's going to have to be a huge circle. It's going to go way outside of the camera range, and it's enormous. But the curvature for this point would also be given by 1 over R. And this one, its curvature is going to be given by 1 over this R. Now since this R is smaller, 1 over that is going to be larger. So this K is larger than this K. So maybe I'll call this R1, that's K1, and this is R2, and that's K2. Since R1 is smaller than R2, when I take reciprocals, that flips. 1 over R1 is 1 over R2. If this is smaller than this, and I take 1 and I divide it into this number of pieces, here's a special case that always helps people understand this. I know that 2 is less than 3. Let's think about how 1/2 and 1/3 compare. If I take 1 and I divide it into 2 pieces, those pieces are going to be larger than if I take 1 and I divide it into 3 pieces. So it's going to go the other way. So the one with the larger or the smaller radius has the larger curvature. This is the curvature at this point, and this is the curvature at this point. And this one it definitely has an even larger radius. So it's going to be the smallest curvature of them all. Now, if I tell you that curvature is a measure of curviness, that's intuitively true, but people are going to say, well, what do you mean? It's not very technical. Could you please give me a technical definition? What do you mean by curvature? Well, what we mean by curvature, or the way we measure this sense of curviness, is to look at the unit tangent vectors. So if I draw a bunch of unit tangent vectors over here, now I know their initial points are starting at different locations, but if I drew them tangent to the curve like I'm supposed to, if I drew them with their initial points at the same location, these are basically pointing all in the same direction. The unit tangent is not changing very much at all here. Or if I look at the unit tangents over here, notice how fast they're changing directions? The unit tangent is changing a lot. And here, it's changing some, but not nearly at the rate that it's changing over here. The unit tangents are changing a lot. It's turning very quickly, and that's because the curvature is large. So we're measuring this curvature, this sense of curviness, by looking at the unit tangent vectors and seeing how they change. Now we want to be careful. We're not seeing how they change as time changes, because this curve could be parameterized in a lot of different ways. I could travel along this curve at 1 speed, and I could travel along the same curve at 5 times the speed, and it would be the same curve. So the speed could change from parameterization to parameterization. It might take me 5 times as long with one parameterization to get across this curve, to go from here to here, than it would with a different parameterization. So we don't want to think about speed. We don't want to think about motion. We're thinking about geometry. We're saying, how does the unit tangent change as we move along the length of the curve? So I'm going to use the arc length parameter S. So this is the definition of curvature. This is our more precise definition. We take a look at the unit tangent. We say, how does it change instantaneously with respect to arc length? And then we take its magnitude. And that's going to be a number. And since it's a magnitude of a vector, it's always going to be greater than or equal to 0. If kappa equals 0, it's a straight line. Straight line motion. Nothing's going on. You're just going in a straight line. If kappa is non-zero, you're turning a little bit. Now, in the first video on curvature and torsion, we derived 4 more formulas for curvature. So this is the first one, but we don't really use it. So we had the first one plus 4 more formulas. And they applied in different circumstances. So one was the derivative of the unit tangent with respect to time over the derivative of r with respect to time. You take the magnitudes of both of those. So that's one way of calculating curvature. If I already have to calculate t hat, this is probably the way to go. Another one is sometimes written this way. It's acceleration crossed with the velocity vector divided by the speed cubed. Now sometimes instead of thinking in terms of those vectors that represent motion, I might want to just think about this in terms of r and r's derivatives. So this is r double prime cross r prime, want its magnitude, and then we're going to divide by the magnitude of r prime cubed. But that's just the magnitude of the cross product of acceleration with velocity. So this is the part of the acceleration that's pulling in a perpendicular direction to the velocity, but then it's been rescaled by dividing by this velocity cubed. Not the velocity cubed, excuse me, the speed cubed. So we get this over here. So that was curvature. And then we had 2 more versions of this in special cases when we were in the plane. But I'm just going to list these 3 for right now. If r of t is x of t, y of t, we had a formula for that. And if y was given as a function of x, we have formulas for that. So that was what curvature was, and these are 3 of the 5 formulas that we used in the first video to, or that we talked about using to calculate curvature. We haven't actually practiced yet in any of our videos. On the last video, we introduced a new quantity called torsion, and that was all related to the Rene frame. Now remember, the Rene frame is just your TNB frame. So here's the x-axis, here's the y-axis, and here's the z-axis. And, excuse me. Oh, I wrote x-axis, y-axis, and z-axis. It looks just like the x-axis, y-axis, and z-axis. But the Rene frame is made of unit vectors. And instead of the x-axis, we've got t hat. This points in the direction of motion. So if we're moving along the curve, t hat points in the direction we're going. I'm sorry, guys, I'm just not feeling very well right now. Thank you for understanding. Now, the unit normal always points to the left of t hat in this right-handed coordinate system. The unit normal points in the direction that we're turning. So this is the unit vector that points in the direction that we're turning. And remember, we said earlier the acceleration vector is some linear combination of t hat and n hat. So the acceleration vector lives in this plane. It's got some component that's parallel to t hat, and then some component that's parallel to n hat. And I'm sorry, that doesn't look very parallel, but that's the idea. Here's a sub n times n hat. This is a sub t times t hat. When you add those together, you get this acceleration. Acceleration is always in the plane that's defined by t hat and n hat. The binormal vector, b hat, is perpendicular to that plane. So this is a unit vector. Perpendicular or orthogonal, or when we're talking about planes, we usually say normal. But I'm not going to use normal because we're using normal for something else. So I'm just going to say the unit vector perpendicular to the plane, containing the acceleration vector, which also contains n hat and t hat. Okay, so we've got this little moving reference frame. It goes with our particle everywhere it goes along the curve. So if this is our curve in three-dimensional space, here's my x-axis, y-axis, and z-axis. If my curve looks like this, then t hat points in the direction we're going, n hat points in the direction that we're turning, and b hat points out of the page at us because of the way I drew this picture. By the right-hand rule, b hat's going to point out of the page. So we've got this little moving reference frame that goes with us everywhere we go. This is the world from the perspective of a particle traveling along the curve. Okay, so as time changes, or as the arc length changes, as we move along the curve, this whole reference frame changes. And the rates of change of that reference frame are described by the Rene-Seurat equations. And I'm just going to write down the versions where we have unit speed. The derivative of t hat with respect to arc length is just going to be the curvature times n hat. So if b hat is pointing out like this, t hat goes this way, and n hat goes this way. T hat prime is orthogonal to t hat and parallel to n hat, and as t hat goes that way, n hat goes that way. So if our curvature is positive and torsion is 0, that's what we're going to see. The binormal just points straight up and we're just turning. So the rate of change of this guy is parallel to this guy, and that rotation rate of this whole plane, it's called the oscillating plane that contains t hat and n hat, is given by the curvature. Then the unit normal is also changing, and its rotation rate is the negative of the curvature times t hat. So this derivative and this derivative and t hat point in opposite directions. So we've got that. Now, if we also have some torsion, so we're twisting out of this plane that we're in, then the pictures look something like this. So assuming for a moment that curvature is approximately 0, if we're twisting out of the plane that's down here, the oscillating plane, but we're twisting out of it into a new plane, then the derivative of n hat is going to point up, the derivative of b hat is going to point in one direction. And it turns out, because of a strange sign convention, just an artifact, that torsion is negative whenever the unit normal is chasing the binormal. So the unit normal is going towards b hat. So in general, the derivative of b hat with respect to arc length is given by the negative torsion times the unit normal. So here's the normal, here's the derivative of b hat, and they point in opposite directions. So we see this negative torsion here. Now, this guy is also going to have a component that is given by sort of the opposite of this. If this one is moving away, that one's moving towards. So we're going to have this. So those are the Rene-Seurat equations. They tell us how this little frame of reference moves as time increases, as we move along the curve. Now, we want to review one more idea. If curvature is positive, it leads to turning to the left like this. If torsion is negative, the unit normal moves toward b hat. So we're sort of twisting out of this plane. If this is my frame, the left side comes up, the right side goes down when torsion is negative. If this is my frame, the right side goes up and the left side goes down when torsion is positive. So when torsion's positive, b hat is chasing n hat, not the other way around. So torsion is leading us to twist out of the plane we're in and into a new plane, either by twisting this way out of the plane or twisting this way out of the plane. And curvature is just us turning left and right, like we're turning in our bumper car and our binormal is pointing straight up. Now in general, you could have both. You could be twisting out of the plane at the same time that you're turning. And so the whole frame would look something like this, but it's going to look a little different because you're translating along the curve the whole time. I lost some of the papers. Excuse me. Okay, so that's what's going on. Curvature is positive means we're turning. T hat moves towards n hat. And that is always going to happen because n hat's always pointed in the direction we're turning. So t hat is always going to move in the direction of n hat. Now, if torsion is non-zero, we're twisting out of the plane that we're in. And into a new plane. If torsion is negative, n hat moves toward b hat. And it's like, I don't know, unrequited love. N hat moves toward b hat and b hat moves away from n hat. N hat is set. N hat tries to keep chasing this one, and this one's like, no! And so it just, the chase never ends. This one chases this one, and this one goes away, if torsion is negative. Now, if torsion is positive, it's the other way around. So b hat moves toward n hat, and n hat moves away. We experience this when we're looking at that normal plane as shifting to the left and to the right. So again, here's our little model. We are like leaning left when b hat's chasing n hat. We're leaning right when n hat's chasing b hat. All right. Now, we talked about all those ideas, but I did not give you a way to calculate torsion. Now, it turns out that since this is true, we've got this Rene Seurat equation. So let's say our torsion is over here, and b hat prime is that way, b hat's pointing straight up, n hat is over here, and as b hat goes that way, n hat goes that way. So this one's changing in this direction, that one's changing in that direction. And this is with negative torsion. B hat prime and n hat are always parallel to each other. And in the last video, we derived this fact. B hat prime is speed times negative torsion times n hat. So if I want to get torsion by itself, basically what I need is the length of this vector. So I want the length of that projection onto here, but then I want to divide by the negative speed. So torsion is the signed, so plus or minus, length of the projection of b hat prime onto n hat. But remember, the projection of b hat onto n hat, that length of the projection is just a dot product. So that's b hat prime dotted with n hat divided by the length of the vector we're projecting onto, but n hat has a length of 1. So we just have this, but we also have this extra factor of speed. So we've got to divide everything by speed. Or negative speed. Oh gosh, it's an abusive notation. Say negative speed, negative speed. It looked like a velocity vector, but it's actually the magnitude of velocity. Okay, so this is 1, and torsion is, let me write it more simply. Now the signed length of this projection, the length is going to be this number times plus or minus 1, and that plus or minus 1 is going to depend on the relationship between b hat and n hat, if they're pointing in the same direction or the opposite direction. The dot product will take care of whether they're pointing in the same direction or the opposite direction. So I don't really need this if I drop the absolute value. So what we get is negative 1 over the speed times the derivative of b hat with respect to time dotted with n hat. This is one formula for torsion. Now, this formula can be used along with another formula to derive the next formula. Now, my students are being given extra credit to do this derivation. I will post the full solution of the derivation in another video, but I will just say that the next formula that I'm about to state, the formula for torsion that we actually use, is derived from a couple of formulas. So this is a definition, but we don't use this. We're going to use this other one instead. It can be shown that b hat is actually r prime cross r double prime divided by the magnitude of r prime cross r double prime. That looks a little strange. It says, okay, take the velocity and the acceleration, cross them, and then divide by the magnitude of that. That's going to be your b hat. And you're like, okay, that's pretty cool. You can prove that. My students have to prove this for extra credit. Now, using this fact, so we're going to use this fact and this fact. we can show that torsion is given by this other formula. Now this is the formula that we use. You take r prime and you dot it with r double prime cross r triple prime. And you're going to divide all of that ooh. I don't even know if I have that written down anywhere. Let me see. I don't want to tell you the wrong formula, so I'm looking it up to make sure that that denominator is exactly what it's supposed to be. Ah, that's what I thought. It's the cross product of r prime and r double prime squared. All right, now this numerator, remember that looks like u dotted with v cross w. Remember that was the volume of the parallelepiped that we studied earlier this semester? That's given by a 3 by 3 determinant. R prime is in the first row, R double prime is in the second row, and R triple prime is in the third. And then we're going to take R prime and R double prime, cross them, find the length, and then square it, and that's going to be your torsion. Now, the proof is important. It's very important that we are able to get from this to this and then use that to get to this. But we just don't have time to do that derivation in class. So I'm going to put the video online after I give you guys an opportunity to get the extra credit. So here's your extra credit assignment. Prove that this is true. Then I want you to show that torsion equals that. This formula. Using this formula that you've just proven. And the fact that torsion is negative 1 over the speed times b hat prime dotted with n hat. With those two pieces of information, this piece and this piece, you will be able to show that torsion is given by this. You're going to have to use a lot of vector identities to do that. So there's a lot of product rule involving cross products and dot products. You're going to have to keep those in mind. So it may take a little bit of work. You also have to remember this other fact. And we used it earlier when we showed that b hat prime had to be parallel to n hat. If two vectors are parallel to each other, their cross product is 0. And we know a lot about vectors that are parallel given our frame. Like we see in this picture, n hat prime is parallel to b hat in the special case when the curvature is, well, near 0. I guess that's actually the worst example possible here. b hat prime is parallel to n hat. T hat prime is always parallel to n, but n hat prime actually has two components. One that's in the direction of the unit tangent and one that's in the direction of b. So this one is the only one that's a little wonky because it's a linear combination of two other vectors. But this guy is parallel to n hat, and this guy is parallel to n hat as well. So you're going to use that fact. Anytime you see a couple of parallel vectors here, you're going to immediately know something is the 0 vector, and that's going to simplify everything really nicely. And then after lots and lots of simplifications, it took me just a few pages, 2 or 3 pages, to derive this myself. You'll get to a point like this. So this extra credit is due next week, and after I accept the extra credit next week, I will post the video showing the derivation of this online. Now let's use some of our formulas. We've been talking about curvature and torsion for a long time, but we haven't really used them. Now this formula looks pretty involved, and it can be pretty involved. even if r prime is relatively simple. But if we have a particular t value or a particular location, and when I say t value, I mean a particular time. If we have a particular time and a particular location, or a particular location that is associated with a particular time, this is just the determinant of a 3x3 matrix with a bunch of numbers in it. And if those are numbers, that 3x3 determinant is easy to calculate. This is a cross product of two vectors made of numbers. Cross products are easy. We can find lengths of vectors pretty easily. We can square lengths of vectors pretty easily. So this really is not as complicated as it looks. It only gets complicated if we leave all of this in terms of t. Now, there are going to be some very nice functions that our textbook authors like to use, where everything cancels quite nicely. So we're going to look at some problems like that. Now, notice the presence of r triple prime in this torsion formula. R prime is velocity if r is position along the curve. The second derivative is acceleration, and the third derivative is jerk. So if you have a 0 jerk, so that means your acceleration vector is constant. So this is 0, 0, 0. Then the determinant of this 3x3 matrix is 0. So you can't have torsion with a 0 jerk. If you have a 0 jerk, torsion is immediately 0. And that means your curve is staying in the same plane the whole time. Remember, torsion equals 0 means planar motion. Torsion non-zero means you're moving out of one plane and into another in that particular moment. So if r triple prime happened to be the 0 vector all the time, then we know that our curve is lying in a particular plane. It wouldn't necessarily have to be the xy plane. That's the way we tend to think of it. It could be the yz plane. It could be z equals 7. It could even be something like 2x plus 3y minus z equals 15. If it lies in that plane the whole time, the torsion is going to be 0. But if it's moving out of one plane and into another plane, then we're going to have a non-zero torsion. Okay, so let's practice some. So I'm going to make up a vector valued function right now on the spot. Hopefully I don't make up one that's too terrible for us. I'm going to do something that looks pretty simple to me. We'll see how bad it is. Let's say this is t squared times I hat plus 3t cubed times j hat minus t to the 4th times k hat. In component form, we just got t squared, 3t cubed, and negative t to the 4th. And let's say we want to find t hat, n hat, and b hat at a particular point. Let's say at the point 4 and then 24 and negative 16. So we want t and b at that point, and let's also find curvature at that point and torsion at that point. Now, curvature and torsion actually might not be that bad in general, not just at this particular point, but they might be simple functions of t. So we might find these as functions of t first, and then find out what the curvature and torsion would be at that particular time that leads us to this particular location. But these guys, they can be sort of difficult to calculate. The derivative, or n hat, is difficult to calculate given t hat. Not because differentiation is difficult, but because you're going to have the speed in the denominator for t hat, and then you're going to have to differentiate that and find the magnitude of that derivative and divide by it. It's just a lot of algebra. So we are going to do this at a particular time, but these two I think I want to do in general. So I'm going to find these as functions of t first, and then we'll find out what the curvature is at this location. So this is a location, remember that. This is x naught, y naught, z naught, and it's associated with a particular t naught. We're going to find that later. But for right now, let's just say we want to find curvature. And we had those 5 formulas for curvature. I think, given the circumstances, given that we also want to find torsion, it makes the most sense to use the one that involves r double prime and r prime. So we're going to do the magnitude of r double prime cross r prime, all divided by the speed cubed, or the magnitude of r prime cubed. And then torsion has r prime in the first row, r double prime in the second row, r triple prime in the third. I'm going to find the magnitude of that. I'm going to divide by the cross product of r prime and r double prime. We're going to take that cross product, we're going to find its length, and then we're going to square it. Notice we also need that quantity for the numerator of curvature. Now I know those are in the reverse order, but the magnitude of u cross v is the same as the magnitude of v cross u. They just have opposite directions. So this length is actually equal to that length. So that quantity, once we find it, can be used twice. So let's do curvature first. So for curvature, I need velocity and acceleration. So here is my r of t. R prime, that's velocity, is 2t and 9t squared and negative 4t to the third. R double prime, it's 2 18t and negative 12t squared. Okay, now according to this formula, there are 2 things I've got to do. I've got to find r prime cross r double prime, or r double prime cross r prime, and then I find its magnitude, and then I find the speed and I cube it. So I think I'm going to do the cross product first. R double prime cross r prime. So I put r double prime in the first row, r prime in the second row. We're going to find the magnitude later, so it'd be okay if you reverse the order. But if you weren't reversing the order, if you're interested in the direction, this order matters. Remember, for cross product, u cross v and v cross u are opposites of each other, so you're going to get the opposite answer if it wasn't a magnitude there. All right, so let's do the cross product. I cross out this row and this column. I get this times this. So what that's negative negative 40 minus 32. So that's negative 72 t to the fourth minus a negative 9 times 12. What's 9 times 12? That's 90 plus 18, 108. Also t to the fourth. So then when you combine these, I think you're going to get 36 times t to the fourth right there. Then cross out the row and column containing j hat, and you're going to have this times this. So you've got negative 8t cubed minus this times this. We're subtracting a negative, so that's adding 24t cubed. 24 minus 8 is 16, and then we multiply by negative 1, so we're going to get negative 16t cubed. Cross out the row and column containing k hat, we get 18t squared minus 2 times 18 t squared. So that's just going to be, I should have written that up over here, negative 18t squared. Sorry, I sort of did that in the reverse order. I simplified up there instead of down here. Okay. So that is our double prime cross r prime. The magnitude is kind of ugly. Got 36 t to the fourth squared plus negative 16 t cubed squared plus negative 18 t squared squared. Actually, I think I would like to use a calculator for arithmetic on this. Oops, I guess I don't. I can't use one. I don't have one anymore. I gave mine away recently. Alright, that's okay. But we would use the calculator for arithmetic, and we square the 36, and we square the 16, and we square the 18. Actually, I can use the calculator on my phone for the arithmetic. I know, some people are like, Ms. Townsend, you should know how to do 36 squared in your head. I'm like, yeah, maybe I should, but I don't think so. I think there are more important things to learn. Okay, so this is 1296, and that's going to be t to the 8th. And then 16 times 16 is 256. So I've got 256. T cubed squared is t to the 6th. And then 18 times 18 is 324. That doesn't really help us simplify much, but this is what we've got here. I guess we could take out a t to the 4th from everything. And the square root of t to the 4th it's going to be a t squared. But still doesn't simplify things very much. You can see why people prefer to just plug in numbers, plug in a t value as soon as you can. So that's our numerator for our curvature formula. Our denominator was the speed cubed. So we need to find speed. Remember how we do that? We take the components, we square them, add them and take the square root, and then we're going to cube both sides. Cube this and cube this. So I'm going to think of all of this as something to the 3 over 2 power. Using our exponent properties, the nth root of x to the m is x to the m over n. Alright, so I've got 4t squared plus 81t to the 4th plus 16 t cubed, or no, sorry, t to the 6th, all to the 3/2 power. And we could factor out a t squared from that. And you're raising everything to the 3/2, so that gets raised to the 3/2 and that gets raised to the 3/2 because of this property from algebra. If I have a product raised to a power, I raise the first thing to the power and the second thing to the power. So this is going to be t squared, which is positive, and then you're going to take the square root of that. It's going to be the absolute value of t, and then you're going to cube it. So it's that applied to that. If you don't want to simplify this, that's totally fine. Okay, so this is our r prime cubed, and that's going to go in the denominator. And I'm going to use another sheet of paper. So I got a little calc 2 there. I'll try to recycle where I can. Reuse, really. excuse me. So curvature as a function of t is this. It was this magnitude, oops, that's just a single prime, divided by the speed cubed. And I've got t squared times all of this. And we're dividing by the absolute value of t cubed times all of this. So that's curvature as a function of t, but if I wanted curvature at a particular location, well, I just need to find the t value that's associated with that location. Alternatively, we could have found r double prime and r prime at that location. So we were asked for the curvature at this point, 4, 24, negative 16. That's an x, a y, and a z. And we know on this curve, x of t, y of t, and z of t are given by the following formulas. T squared, 3t cubed, and negative t to the fourth. Well, if this point is truly on this curve, then there has to be a single time when t squared is equal to 4, and 3t cubed is equal to 24, and negative t to the fourth is equal to 16. Well, according to this one, t has to be plus or minus 2, right? Now, according to this one, well, if I divide both sides by 3, I get t cubed equals 8, and that means t must be positive 2. So positive 2 works for the x and the y. When x equals positive, or t equals positive 2. Oops, that should be a negative 16. Is negative 2 to the fourth equal to negative 16? It is. So it looks like t naught, our time, is 2 units, or 2 seconds. Okay, so if I want curvature at this location, I plug t equals 2 into this. And of course, 2 of those cancel with 1 of those, or 2 of those, of course. And this is going to be your answer. Now, I would simplify this, but I don't have my calculator, and I really don't think it's worth it to do the arithmetic on this video about Calculus 3. So, of course, you would want the simplified answer for this. Now, let's do torsion, and let's not do it as functions of t, because we saw how ugly that got so quickly, even though we were only working with monomials and powers of t. So let's do torsion, but let's see how easy it is when we're evaluating all of this at t equals 2. So torsion at t equals 2 is going to be r prime of 2, r double prime of 2, and r triple prime of 2. It's going to be that determinant. And then we're going to divide by r prime at 2 crossed with r double prime at 2, and it's going to be that magnitude squared. Watch how fast this is. I've already calculated these derivatives, so I'm just going to plug in 2. R prime at 2 is this function evaluated at 2. So I've got 2 times 2 is 4. 9 times 2 squared, that's 9 times 4, which is 36. And that's 2 cubed, which is 8. 8 times negative 4 is negative 32. Our double prime at 2, well, that's 2. 18 times 2 is 36. This is going to be 4 times negative 12, so that's negative 48. Now I actually need our triple prime at 2, so first I need our triple prime at t, because we didn't need jerk for curvature. Derivative of 2 is 0. Derivative of 18, t is 18. And the derivative of this guy is negative 24t. So our triple prime at 2, the constants stay the same, and then 24 times 2 is 48, so that's negative 48. All right, so I've got this vector, and this vector. That's going to go in my determinant. Gosh, I'm wishing I had that calculator right now. I don't want you to think that your math teacher can't do arithmetic. I can. I just don't do arithmetic with larger numbers. Not even large numbers. Like things like 48 times 36. I don't do that quickly in my head. I spent more time learning algebra and symbolic manipulation. Okay. So we can expand along any row or column that we like. I think I want to expand along this one. If I expand along this one, remember the sign convention, it's plus, minus, plus. Always pick up where you left off. Minus, plus, minus, plus, minus, plus. So we're going to have plus 0 times something, and it doesn't matter what that is because we're multiplying it by 0, minus 18. Cross out the row and column containing that 18, and you've got a 4 and a 2, and a negative 32, and a negative 48. And then you have plus a negative 48 times, cross out that row and that column, 4 and 36, and 2 and 36. Okay. This actually isn't too bad because I chose that. I chose it so that we'd get to use that 4, 2 a lot. So this guy is 0. It's gone. So I've got negative 18, excuse me. And then 4 times 48. So 4 times 50 is 200, and then I'm subtracting 8 from that. So 192 minus a negative. So that's minus a negative 64. And then we have a minus 48 times 4 times 36. That's 120 plus 24. So 144 minus 2 times 36, so 72. So now I've got negative 18 times this. And that is negative, let's see, 192 minus 64. I'm super old school. Okay, so I've got 8 and 12 minus 128. Keep the sign of the larger number. The larger was 192. And then these guys, 144 minus 72 is 72. Now again, I could do all that arithmetic for you, but I don't think that that's particularly insightful. So I'm going to use my calculator. 18 times 128 equals 2,304. You don't even have to write that down if you're doing it all in your calculator. Minus 48 times 72. So that's 1152. So it turns out to be 1152. Okay, that's our numerator. Now I just need this cross product evaluated at 2, what t equals 2, and then I want to square it. So I find this vector, and then I find its length, and I square it. Okay. So r prime at 2, we calculated earlier, that was the vector with components 4, 36, and negative 32. Our double prime at 2 is the vector with components 2, 36, and negative 48. And we want the cross product. t equals 2. So I've got a 4, a 36, and a negative 32, and a 2, a 36, and a negative 48. All right. So I cross out the row and column containing I hat, and I get 38 times negative 48 minus a negative is plus 32 times 36. This minus that is right here, minus. Cross out this row and this row and this column, so we have 4 times negative 48. Minus a negative is a plus. 2 times 32 is going to be 64. Cross out that row and that column, 4 times 36 minus 2 times 36. All right. So I've got 36 times 48. That's negative 1728. And 32 times 36 is positive 1152. So we get negative 576 for the x component. And here we've got negative 4 times 48, so that's going to be a negative 192 plus 64. So I get let's do 64 minus 192, 128. Okay. And then this guy, 4 times 36 minus 2 times 36 is 2 times 36, which is 72. Okay, so that is the vector we need to take the cross product of, and then we want it, or that's the cross product, excuse me. We need this length squared. It's a prime. Okay, so I've got 576 times 576. Oops. So I get this huge number. I'm really missing my scientific calculator right now. 128 times 128. And then 72 times 72. And when you add these guys together, you get 53,824, and that was the magnitude squared. So torsion is that numerator, which had those 3 vectors in it, our double prime, or our prime, our double prime, and our triple prime, divided by this. And that's going to be this 5,000 or 53,824 in the denominator. And the numerator is on a different sheet of paper. And I lost it. I don't know where I put it. I just had it a second ago. I don't know. So the numerator, whatever that was from before. So you just divide those, and that's going to be torsion.